In this video, we're talking about two sections, measuring segments and midpoints. So first of all, we're going to talk about the word between, because in math, we have to be very specific about what we mean by between. In English, we kind of use that very loosely, and it can, we know exactly generally what it means, but in math, if we say B is between A and C, then first of all, we mean that A, B, and C are collinear. So collinear means they are all on the same line, so that's important. They have to be on the same line. And what we mean is that AB, the distance from A to B, plus the distance from B to C, add up, the total sum is equal to the distance from A to C. Okay, so that's what we mean by between. By the way, this is not a typo. This means if and only if. Oh, I almost put two F's for that. If and only if, and then we'll talk about the if-then way of writing things in just a minute. But that means that this statement can be read either forwards or backwards. So I can say B is between A and C if I know all this information. Or let's say I'm just given this information, then I can conclude that B is in between A and C. So it can go either way. So now let's talk about measure. I used the word measure when I was describing between. The length of a segment AB is written as those two capital letters without a bar over it. Okay, so when you see AB without a bar over it, that is meaning the distance between A and B. Okay, and distance is always positive. I don't know if you can see that. There you go. Now it's brighter. Distance is always positive. So please keep that in mind as you're doing your work, that first of all, if you say AB, then you're looking to say, oh, it's 10 inches or something like that. But if you're saying AB with a bar over it, you're talking about the object, the segment AB. Okay? So it's a slight, subtle difference, but please make sure you are using that difference. Okay? Now we're going to talk about the ruler postulate. In geometry, we have definitions, which we've been dealing with so far, and definitions just tell us what things are. A postulate is a statement that is assumed to be true. Okay, so it's almost like a definition. It's like when we say, this symbol represents 2. Okay, the concept of 2. So no one's really disputing that. We're just creating that, and we're saying that that has to be true. We're assuming that to be true. Okay, so the ruler postulate, all this says is, okay, the points on any line can be paired with real numbers. So that given any 2 points, and we're talking about in this specific situation, P and Q on a line, P corresponds to 0, and Q corresponds to a positive number. So it's really just like when you think of measuring something with a ruler. What do? We take a ruler, we line it up so that 0 on our ruler lines up with that first dot. Okay, and then wherever that second dot hits our ruler, say that's 7, then we know that that distance is 7 inches. That's all that's saying. Okay, it kind of is like duh, but that helps us connect these objects that are just floating in space to actual numbers that we can use and quantify with numbers. And then we've already talked about this, right? PQ represents a number, and then PQ with a bar over it represents a segment, an object. Also keep in mind that this is talking about a positive number. So if we were measuring from B to A, so going backwards, I mean, we would simply, if we were taking a ruler, we would line up the 0 on our ruler over here and then measure over here, okay, to get a positive number. or you could just take the absolute value. So now let's talk about midpoints and distance formula. Okay, first of all, a midpoint. Lots of different conceptual ways to envision a midpoint, and I will do an exact definition at the end of this video. But basically, it's a point that divides a segment in half, right? So it's the middle point of a segment. The midpoint of PQ is the point between P and Q such that PM and MQ are equal. So if I were to draw this out, I'm going to draw segment PQ. So if M is my midpoint, I want it to, if it's the midpoint, then it has to be located in such a way that this distance from P to M is the same exact distance as from M to Q. Okay, and that makes sense, right? It divides it in two equal pieces. Okay, so our midpoint formula is right here, and this is if we had 2 points. All right, notice what we're doing here. We're taking 2 x coordinates, adding them together and dividing by 2. That's another way of saying I'm averaging the x coordinates. And over here, if I take y1 plus y2 over 2, I'm just averaging the y coordinates. So the midpoint formula is just averaging. And that makes sense, right? We're trying to find the middle, so we want the average. Okay, so for example, if I had the coordinates 2, -3, and 5, -5, this would be my x1, y1. This would be my x2, y2. And then I would plug these points into my midpoint formula. So that would be 2 plus 5 divided by 2, comma, -3 plus -5 divided by 2. So simplifying that, that would be 7/2. And then this would be -8 over 2. As a decimal, 7/2, that's like 3.5, comma, -4. So I know that that coordinate, 3.5, comma, -4, would be point M on my coordinates. Okay, so the midpoint formula really connects the points and lines in geometry to a coordinate plane. Okay. Another way to think of this, I'm going to grab a grid from here. If I were to graph these points, 2, -3. Actually, I want to use different points. Let's say I have 1, -3. I want it to come out a little nicer. So I have the point 1, -3, 1, 2, 3, right there. And then I'm going to have 5, -5. 1, 2, 3, 4, 5. 4, 5. Okay. And if I draw a line through them, okay, so let's call this point P, and that's the coordinates 1, -3. And then this is Q, and that's the point 5, -5. If I wanted to find the midpoint, and if I had to estimate it, I would say it's roughly there, right? But if I wanted to be super exact, so that I know exactly where it was, then keep in mind that the midpoint has to be collinear with P and Q. It has to lie on that same line. So what do we know about lines? Well, we know that we can find the slopes, correct? So if we count the slope from P to Q, so this is going down 2 and over 1, 2, 3, 4. So down 2 and then to the right 4. That's the whole slope from P to Q. So rather than doing down 2 over 4, if I wanted to get the midpoint, I would do half of that. So for the midpoint, I would go down 1 over 2. And that's actually where we predicted the midpoint would be. So I can visually see that the midpoint is at 1, 2, 3, comma 1, 2, 3, 4. Now you see why I changed it, because I didn't want to have 3.5. Okay, so that's just a visual way to do midpoint. If you have a graph, if something's already graphed, it might be easier than doing the algebra or the calculations for the formula. So 2 ways to do midpoint. Now let's talk about segment bisector. Okay, so this word bisector, the prefix bi we know means 2, just like bicycle. All right, so sector means section. So a segment that is split into 2 sections. So if I split a segment into 2 sections, and we're talking about 2 equal sections, so then that is what we call a segment bisector. So a segment bisector can be a segment. So if I put a segment going through here, let's call this original segment PQ. And then let's call this green segment, I don't know, let's call it AB. All right, so AB, the segment, is cutting that segment PQ in half, right? It's cutting it right at its midpoint M. All right, so AB would be a segment bisector. Okay, it could also be a line. So let's say this didn't stop. I could have a whole line doing that. So AB, the line, could be a segment bisector. Or let's say that line was really this parallelogram, right? And imagine this coming out at you, this parallelogram coming out of the page at you, and it's like this piece of paper coming out. That would be a plane. So in order to label this plane, I would need A and B and then another point. Let's call another point on that plane C. So plane ABC could be a segment bisector. But notice that nothing changed about the segment PQ. PQ was still cut in half. It's just what object cut it in half is what was different. But all 3 of those things can be a segment bisector. Okay? And then the midpoint theorem, the only difference between the midpoint theorem and the definition is just how they describe the midpoint. So they're saying if M is a midpoint, then we know that AM is congruent to MB. So on the previous page, I would have said AM equals MB. Here, I'm using this symbol, the congruent symbol. Okay, so congruent and equal, the only difference between them is equal is talking about numbers. So you see how AM has no bar over it and MB has no bar over it. But over here in that theorem, AM has a bar over it and MB has a bar over it. So I'm talking about the segments themselves. And so when I'm talking about objects in geometry, I use that congruent symbol. That means same size and shape. Okay, so in geometry, we will be doing lots of proofs. And all we mean by a proof is just a logical argument in which each statement that is made is backed up by a statement that is accepted as true. Okay, so what we mean by that is any kind of definition or postulate or theorem that we have learned. Okay, so because of that, we are going to be keeping cards, proof cards, so that we can easily reference all the things that we've been learning, and these will be used in proofs. So what I want you to do is get out your proof cards. And I want you to, for the definition of midpoint, we're going to write this in if-then form. So we're going to say first, if M is a midpoint, then PM equals MQ, and we're going to put a little diagram over on our card so that we understand what's going on. So if we're talking about a midpoint, we are talking about a segment as well. Oh, that should be Q. Okay, so that's one way to write it. Remember how we had that if and only if? Well, that means if we have the reverse knowledge, then we can use this as well. So if PM equals MQ, then M is a midpoint. And remember that we also had that theorem that was talking about congruence. So this would also apply if I wanted to use segment bars and the congruence symbol and segment bars and the congruence symbol. All right, so you don't have to write that. You might want to make a note of that it also applies to congruence. Actually, let's write applies. Applies to congruence segments as well. Okay, so you don't have to put those red lines over on your card. All right, and then a segment bisector. If, and we can put AB, you might want to put in parentheses AB. We typically won't see planes, so I'm not going to worry about planes. So notice that I have either a segment or a line. If AB is a segment bisector, then it intersects PQ, so we're talking about a segment, okay, whatever segment we're bisecting, it intersects PQ at its midpoint. And again, I would recommend drawing a picture. So if I have PQ, let's draw M, and then we're going to draw a line going through that. Notice that that line does not have to look perpendicular or anything. It can just go through there. So AB is a segment bisector if it intersects PQ at its midpoint. And remember, the opposite can be true as well. So if AB intersects PQ at its midpoint, then it is a segment bisector. Okay, so make sure to keep those on your cards. We will use them throughout the year. All right, going back, I did miss one thing in our notes that I wanted to make sure we got. So distance formula, I know you've seen this before. That is a formula that we use to find the distance between 2 points on a coordinate plane. So again, I'm going to show you 2 ways. I'll use the formula first. So we've got 9, -5, which is right there, and -6, 12. I don't like 12. I'm going to change that right now. Let's call that 10. because my grid only goes to 10. So negative 6, 10. 1, 2, 3, 4, 5, 6, 10. There we go. There's K. There's J. So if I want to know the distance between those two, I can use the formula where this is my x1, y1, this is my x2, y2. And so the distance between J and K, or another way of writing that in geometry, is JK. And so we would use negative 6 minus 9, parentheses squared, plus 10 minus a negative 5, parentheses squared. And then we just simplify. So work inside the parentheses first. Negative 6 minus 9 is negative 15. And then 10 minus a negative 5 is 15. So 15 squared is 225. And then another 15 squared is 225. Add those together. And then we get 450. And then if we simplify that radical, let's see, I'm thinking 9 for sure. And that would be 50. Oh, I know 50 can be broken down as well. So it would be 25 and 2. So this is 3, this is 5, and then this is root 2. So I have 15 square root of 2 is my distance for JK. Now let me show you another way. The distance formula is actually derived from the Pythagorean theorem. All right, so let's say I graph this and I use this distance between J and K as a hypotenuse of a right triangle. So I'm going to draw a right triangle out of this. So in order to draw a right triangle, go horizontally and then vertically. It's almost like you're counting rise over run, almost. All right, so this distance on the bottom is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then this distance along the side is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we can use Pythagorean theorem. So 15 squared plus 15 squared equals my JK, my hypotenuse squared. And then you can see we're starting to see the same numbers. 225 plus 225, which is 450. And then if I take the square root, then I get JK equals the same thing, 15 root 2. All right, so distance formula, 2 different ways to do that. Midpoint formula, 2 different ways to do that. And we have our proof cards all ready to go for when we start doing proofs.